Hello, it's Brad here, and today what I'm going to quickly explain is a little issue that we have in the software. I wouldn't call it a bug because the software is doing exactly what it's supposed to be doing. However, we have some pretty interesting results. So I'm going to go through a design example here and show you what's going on, quickly explain why it's happening, and then give you an idea of change that we're looking at making to the software that'll be available in the next minor release update that will handle things a little bit differently. So starting with this, you'll see we have a shear wall. It's 3 stories, and just to keep the numbers simple and to keep things relatively straightforward, we have 100 kilonewtons being loaded at each floor level. There's some axial load there as well, but you would expect your shear diagram to be sort of stepped. But what actually happens is we get this case where we actually have a higher factored shear that we're designed for at the second story compared to the first story, which is not at all what we would expect. So, I mean, the natural question from that is why would this even happen? So, I'm going to get into that. If you're looking to make this yourself, basically, if you make a shear wall that's 10.2 meters high and you evenly split it into 3 levels, then the software will automatically break them up evenly so you get this configuration. Here are my loads here if you want to get this. So I have 100 kilonewtons and then I have 150 dead load. And like I said, just to keep the numbers simple, that's all that I applied there with self weight left on as well. So basically, when you go through and apply it, these lateral loads are applied, and we get a moment diagram that looks something like that. I'm just going to move it over a little bit, and you'll see the numbers making them a bit more readable. This is what our moment envelope looks like from those 100 kilonewton loads applied at each location. So now if we take a look at the results from the multi-story module, you'll see the factored moments that we're designing for. All right. I mean, I feel like that makes relative sense there. And then comparing those to the resistances, we can actually get those if we go through and look at the interaction diagram. So you'll see I've sort of overlaid the PM diagram here. You see the envelope curve here. And so at whatever axial load we're looking at, we can compare to get those moment resistances. So you'll see on the x-axis here, it's where we have our moment resistance. Axial load is the y-axis. And so we have these same numbers here that we saw in our moment envelope curve. So those are what the different stories are being designed for. And then if we compare that to the resistances, we basically move horizontally at the same axial load to get these values here. And so now if we go and we compare them, so looking at comparing each factored moment to the moment resistance, you can see that the base of the wall, which is really what we're designing for, is a lot closer to this envelope curve, which I think makes sense. That's going to be the critical section of our design. And so at this height, you can see we have a 14% some daylight there between our factored moment and our resistance. I'll get into a little bit later why that's important. But you'll see as we go further up, we get more and more flexural over design. And that's just because we're using the same design that was based on what we needed at the base to construct the rest of our wall. Just as a little bit of review to show you why we care so much about these moments, basically, I'm going to be explaining this for conventional construction. I have a clause from CSA, the S304 2014 edition, where 16.5.4, this is talking about conventional construction shear walls. There are similar clauses for other SFRS force modification levels, basically. So if you have higher ductility, there are similar clauses that have similar inputs that are a little bit different. But just to be basically keep it simple, I'm just doing conventional construction today. So if you take a look at this clause, there's part A and part B. So if we're looking at part A, basically it's looking at, so the shear corresponding to the development of factored moment resistance of the shear wall at its critical section. So what does that mean is we're basically asking, okay, we have a factored shear. We ask ourselves, how much would this shear need to be increased so that the wall is for sure going to fail in flexure? So what you can picture is if we amplify this force, how much do we have to do that to get our moment envelope for our factored moment to actually reach our resistance? So if we do that, because we do want that flexural ductile failure compared to a brittle sudden diagonal shear failure, basically we have to scale it up by the factor of what our resistance is to our factored moment. And basically by bringing these to be the same point, that is how we figure out how much we need to scale our shear forces up by. The second requirement, part B, is basically asking what would our loading look like had instead of using our RO and RD SFRS force modification factors, if we just use 1.3 as the product, how would that affect our loads? And so I have a little table here. I mean, you can see our different ductility factors, 1.5, 2, and 3, and the same overstrength for all of them. But then if we go and look at how much our forces increase from that, for conventional construction, that'll give us a 73% increase, basically by looking at what this product is compared to that product of 1.3. So then if we go through, we have these two limits. I mean, we have part A and we have part B. So we basically look at the smaller of these two values that we have here. So we check part A, which is where we ensure flexural failure by scaling up our shear. But then we also look at this, what that force would have been had we used RDRO of 1.3, and then we just take the smaller value of those. So we just use whichever of those is less. So going back to our elevation here, so we have our loads, and this is probably the shear envelope that you would have expected. So that if we're going through and we're doing this, showing before the info from our interaction diagram, we have these different degrees of overdesign from part A. And so if we apply those basically, so at the bottom story, 14%, if we go through and do that, you could see we need to scale these up by different amounts. And this is basically looking at each element one at a time. And then if we go and look at part B, so since we're conventional construction, we have that 73% increase. So we have that for all of these as well. And of course, what we're going to do is take whichever one is less. So then you'll see what happens is, since we're really designing for the base story when we chose our cross-section for flexure, we get this much lower percentage, whereas when you get to the higher ones, we get 73% because it governs over the flexural overdesign that we have. And so then that is how we end up with this ridiculous curve along the height of our structure, where our factored shear, for some reason, gets higher further up the wall. Okay, so if I sort of simplify this, this is what we're looking at, and this is what I'm addressing. So you can see how we got here, how the software goes, and it checks each element on its own to sort of consider that. And so what I want to do is quickly zoom out and show you looking at this requirement, starting with just looking at flexure, and talk about the interpretation of that clause and how that could be different, and what we might expect going forward to be a more reasonable level. So what I've done for this wall is I've shown again the moment envelope curve, similar to what we had before. And I have our moment resistance going along the height. You can see we have little jumps where we have axial loads resting on the wall at each floor level. And so once again, we're asking ourselves for that part A, so how much do we need to scale these loads up, all of these loads, so that the bottom point here, that it actually is the same as what the resistance is. So that is basically the amplification that we need to end up with the wall failing in flexure and having that ductile failure. So just for reference, it's relevant to know, we have these two values. So at the base, we have our factored moment, and then the resistance. And so you can see the ratio of those is 1.1409. And so that is how we end up with a 14% increase. So if we compare that, basically if we scale all of these loads up, we had 14% to this top one, 14%, 14%, basically making them, 114.1 by using that ratio. What that does, I've even checked it down here if you're curious, but if we scale these loads up, it basically shifts this entire diagram over so that it lines up right down here. Okay, so that is our amplification that we're using. So now the question is, this is what we were already doing for the base story. Now, does it make sense that we then do this again differently, ignoring what is critical at the base for stories 2 and story 3? So this is where we would argue, no, that would be actually overly conservative. That's what the software does right now. But what we're saying is that that's not something that you need to do, because the critical section, even if we're looking at the shear wall further up, it is critical at the very base. And so it is being needlessly conservative, once again, in our view, to be doing that extra amplification if we're at least doing it for the section that we're most worried about. So then going back to that shear envelope, using that 14%, rather than doing it differently and independently for each floor, we figured out what we needed at the base. So this is what our answers change to if we use that 14% for the entire height of the shear wall. And so hopefully, after sort of going through this, you might look at this and think that it's more reasonable that, okay, we figured out the very base, we are satisfying this clause for the entire wall. And so that is what we're looking at changing the software to for the next minor release. Now, if you have any questions about anything on here, I mean, you can always contact Mass Technical Support. Usually it's me who would get a hold of, Brad, but I mean, anyone in our office is available and capable to answer questions such as these. In particular, dealing with interpretation of a lot of the new seismic clauses and requirements that we have, just for design in general. So you can always contact Mass Technical Support. The email address is there. You can always use the contact form on the website as well. And if you need anything else, feel free to reach out. Thank you.